Hello, everyone. Thank you for inviting me here, and I'm glad to have this opportunity to talk about some of my research and also opportunity to encourage you more into 3D audio production. Well, Josh did a great introduction about intelligent music production and how important psychoacoustics is in, in creating intelligent music. Well, my talk will be focused more on 3D spatial audio perception and how that could be related to intelligent music production and semantic audio also. Right, so I'll give you a brief introduction about how we perceive sounds in 2 dimensions and 3 dimensions, how they are different, and talk about, well, a bit of vertical image localization theories, what's been done in the past and what we've done in the recent years, and also talk about how that research can be related to the development of new 2D to 3D mixing system. And the next thing I'm going to talk about is phantom image elevation effect, and this can be directly used for 3D to 2D downmix cases, and I'll summarize the talk. Okay, Dolby Atmos. I'm sure most of you are familiar with this new cinema format, Dolby Atmos. It's object-based audio format, which means you don't master your mixes channel-based, so you don't have to create a specific channel format. You create all the multi-channel audios, and then you can encode them into audio stream and decode them, and using metadata containing directional information about each object, you can recreate the original impression about the spatial audio in any loudspeaker reproduction environment. So channel-based audio is limited in terms of reproduction system layout, because well, in recording studio, if you produce the music using 5.1 surround loudspeakers format, and then listeners have different loudspeaker format, then the original intention of the producer will be ruined at the user end. But with objective audio, you can recreate the directional information of original mix as similar as possible, because you're relying on the metadata of each object's direction. Another recently developed multi-channel audio format is Aura 3D. It's channel-based, uses height layer and overhead channels to provide more immersive audio. In fact, Dolby Atmos and Aura 3D, they're competing against each other in the market. They're growing gradually. They're basically covering different markets in the world, and Aura 3D is doing really well in India. They're doing, producing Bollywood films in Aura 3D, and it's being received really well in India and other places in the world. But Dolby Atmos is also doing well in other areas. I've recently seen Avengers 2 in Dolby Atmos, which was really great. It was a very good experience, and I encourage you to go to Dolby Atmos Cinema. I don't know if there's one in Birmingham, but there are actually only 2 or 3 around in the UK, but I think the number will be increasing in the near future. So this is the background about background for my talk. Okay, now there are new formats. All these new multi-channel formats employ height channels or overhead channels to provide more immersive audio. That means, from producer's point of view, we need new techniques. We need new recording techniques, mixing techniques, up-mixing techniques, down-mixing techniques. Well, having high channels or overhead channels can be really luxury at home environment because, you know, we are struggling with 5 speakers, and how can we add 4 more speakers to experience this high channel audio? That's a challenge at the moment because actually Dolby Atmos, they developed special speakers that project sound towards the ceiling to benefit from the reflections from the ceiling. So you don't have to have the actual physical high channel speakers, but you make use of the reflections. That's one of their solutions for people who don't have any high channels or when people cannot afford high channel speakers. But here we need to think about what's next in music production and what kind of new techniques we need to use. So when it comes to intelligent 3D music production, as Josh said, psychoacoustics is a very important area. Because if we want to make our system more intelligent, basically we need to understand humans better and make the system to follow how human does. And so there is an important question about what are the most important parameters, most important perceptual parameters that can give effective control of different sound attributes. Well, we can think about different applications related to 3D music production. 3D mixing guide, when engineers do mixing in 3D environment, we can provide some kind of intelligent guidance. Okay, so I want to spread the image vertically, so what should I do? Then the computer kind of recommends and, you know, provide some solutions depending on the sound sources, analyzed in real time, or we can have some kind of audio quality meter for 3D sound production, and automated 3D spatial scene rendering. Well, technologies like SAOC, MPEG-H 3D audio codecs are already available. They have been standardized recently, and they are ready for being used. But the market, the industry is struggling to find the actual user needs and applications at the moment. But when it comes to SAOC, when we have all these objects sent to the user end, the user have all the decoded objects. Now I want to create a certain 3D audio scene. Okay, I want to pan the source somewhere up there. I want to create a more diffuse sound field using my existing loudspeaker system. Then the question is, okay, how do we create that? How do we achieve that aim? The answer is we have to understand what parameters are most useful, what works and what doesn't work. We have to clearly understand that first. So, psychoacoustics. The first question we can ask, how do conventional methods apply? Okay, we use all sort of different rendering methods for horizontal stereo and 2D surround. We have decorrelation methods, panning methods, and blah, blah, blah. So how do they apply? Do conventional psychoacoustic theory be used for 3D music production? Okay, when we talk about localization, when we try to apply panning vertically, okay, the question is, does the conventional amplitude panning like VBUP, can it work effectively? Or can we use delay panning for vertical stereo? Does the precedence effect operate effectively? Precedence effect in terms of concerto acoustics, when you have delay, time reflection with time delay above 1 millisecond, we don't really perceive the direction of source from the reflection direction, but we hear it from the direct sound direction, regardless of the level of the reflection. That sort of thing, can it work for vertical stereo? I'll come to these points later in my talk. And spatial impression. Okay, if we want to create more enveloping sound field, more diffuse sound field, can conventional decorrelation method or delay method be effective for vertical stereos? We have to understand these factors. And also, Okay, let's talk about how we perceive sound horizontally first. Let me remind you with some basic principles. Okay, when we do mono to stereo expansion or 1D to 2D unmixing, basically conventional approach would be you extract ambience from original contents, and then you apply some decorrelation. You make sound more diffused, more uncorrelated, and we perceive wider image, more diffused image. Okay, so when we do stereo to surround unmixing, then we basically use similar methods. But when it comes to vertical unmixing, 2D to 3D unmixing, then what is the best method to create more diffuse sound vertically? And if we want to translate our 3D mix in home environments where there is no high channel or overhead speakers, then what kind of method do we have to use? These are new challenges in 3D music production, and there are actually some commercial rendering softwares, unmixing, downmixing softwares available. They've been developed recent years, but they seem to be relying on conventional principles, conventional methods like PCA, decorrelation, and reverberation, and that kind of thing. So we've been trying to provide some grounded theory, for music production, for 3D music production, 3D recording, 3D unmixing, downmixing, and I want to introduce some of the research outputs in this talk. So we have 2 years horizontally spaced. This is, this is basically how we perceive sound, how we perceive horizontally wide sound, and how we localize sound. Basically, everything is dependent on the interaural differences. The fact that our ears are horizontally spaced is very important. Interchannel cues created between 2 loudspeaker signals, they are translated into interaural cues between 2 ears. But does it happen with vertically arranged speakers? Well, if the speakers are arranged right in the middle, in the median plane, and even if you apply any level difference or time difference, there will be no interaural differences produced between 2 ears. So this basically shows that it would be quite difficult to apply conventional methods in vertical music production because there's no interaural changes. Well, research suggests that vertical perception fundamentally relies on spectral cues like HLTF. But what if our ears are arranged like this? Okay, this is a kind of joke I use, but well, this is actually, if you try this, listening to vertical stereo like this, actually it works. You can apply all these conventional theories, panning methods, and everything. It works fine. Of course, that's natural. Well, our ears are not arranged like this, so this basically shows that we have to think about more perceptually optimized method for 3D or vertical stereo, really. So. Okay, so now I'm going to talk about some past research about vertical image localization and how these can be used for 3D unmixing. Okay, the first principle I want to talk about is the pitch height effect. This principle basically suggests that the higher the frequency of a pure tone is, the higher the perceived image position is, regardless of the physical height of the loudspeaker. So wherever the loudspeaker is, if you play a higher pitched tone, then it will always be perceived higher than a lower pitched tone. That's the thing that was found by Pratt in 1930. That was the beginning of this kind of research, and then this theory was confirmed by many, many researchers over the years. one of the few, the Ruffle and Butler's research is very popular in this context. So if you see this, this diagram, the x-axis shows the actual loudspeaker height, and the y-axis shows the judged image height. So wherever the loudspeaker height is, the image position gets higher and higher as the frequency goes up. So this is what the pitch height effect basically suggests. And this is very specific to pure tone situation when there is a single frequency. But when we have octave band noise stimuli, the situation is slightly different. We still see, well, in this diagram, we see different frequency bands, 125 hertz, 500 hertz, 2K, 8K, and full band. And the black dots show the actual loudspeaker position. And we see general trend of pitch height effect as the frequency band goes up. We see the general position of the perceived image gets higher, but we see some dependency of the image position on the actual loudspeaker position. So in lower band, wherever the loudspeaker is, the image position is around the ear height. The 125 hertz will be perceived somewhere around there, wherever the loudspeaker is. But if you look at the 8K band, the image position kind of follows the actual loudspeaker position, and the localization gets really accurate for the full band situation. The spectrum is wide, and the localization is very accurate in this case. So from this, we can see each frequency band has each unique vertical image position depending on the loudspeaker height. So we've expanded this kind of research for phantom image condition when you have two loudspeakers arranged horizontally, and then you have another loudspeaker layer at about 30-degree elevation angle. So we did this kind of pitch height effect experiment with octave band noise signals for each layer. So we did one experiment with lower layer and then another experiment with the height layer. And the results look like this. So basically the white boxes show the results for the main layer, the horizontal loudspeaker, and the gray boxes show the perceived image positions for height layer. So what we see here is the pitch height effect works up to 500 hertz band, and then it's kind of reset at 1 kilohertz, and then operates again up to 8 kilohertz, and then for 16 kilohertz it goes down again. So this graph shows that the traditional understanding about pitch height effect doesn't directly apply in phantom image condition and also for octave band noise conditions. Well, previous research kind of omitted 1K band and 16 kilohertz band, so there was no data about it, but we found that 1K was actually perceived somewhere around there. But that's partly because 1K is mapped to back perception, according to Blauert's Directional Bands theory. Blauert basically tries to map different frequency bands to different perceptual positions in the medium plane. So he basically suggests that 8 kilohertz is always perceived above the head. 500 hertz, 4 kilohertz, they're mapped for front perception. And 1 kilohertz above 10K, they'll be perceived at the back, regardless of loudspeaker position. That's what Blauert's Directional Bands theory suggests. So going back to this graph, we see this 1K is perceived at ear height position. So that's maybe because of 1K is mapped to the back. So anyway, from this research, we can see some other interesting phenomenon. For phantom image conditions, we observe some elevation of perceived image, which we didn't observe with real image conditions. In all of other previous researches, they used real speakers in the middle. They didn't use phantom images. and the lower frequencies were always perceived around the ear position, regardless of the loudspeaker height. But with the phantom image condition, we hear 125 hertz, 250, 500 hertz, higher than the actual loudspeaker position. So phantom image condition produces image elevation naturally. So I'll come to why this happens theoretically later in my talk. So from this, we propose a novel vertical unmixing method that exploits the pitch height effect based on the phantom image condition. So we basically need to know where each frequency band is perceived in the vertical plane. So once we have the data, once we know where each frequency band is perceived, according to, depending on the loudspeaker layer, we decompose the spectrum of the original signal and into octave bands or critical bands and so on. And then we map each frequency band to each loudspeaker. So, for example, 125 hertz band can go to the lower speaker, whereas 4 kilohertz band can go up to higher speaker. And by this, we can do some flexible mapping of different frequency bands to different speakers in order to create different degrees of vertical image spread. And that can be used for vertical mixing. And the advantage of this method is there is no overlapping of any frequency bands at ear position, because each band is mapped to each speaker. They're going to be combined at ear position. They're not going to be causing any comfiltering or any spectral coloration due to the comfiltering. So a very simple example of this PBA scheme is, okay, let's say we have 3 bands. These 3 low, mid, and high frequency bands are reproduced from the lower speaker, and these same low, mid, and high frequency bands are reproduced from high speakers. And the perceived positions of these frequency bands will be all different. And now we can try to create different degree of vertical image spread. So for example, lower frequency band goes to the lower speaker, and middle frequency bands go to the high speaker, and the high frequency band goes to the high speaker. So eventually when we hear this, this sound, then the overall vertical image spread will cover of this much vertical space. On the other hand, if we send the low frequency and high frequencies from the lower loudspeaker and the middle frequency from the top speaker, then the overall extent of vertically perceived image will be just about this. So in this way, we can kind of control the perceived degree of image spread. And this will be the narrowest condition. So this is the result I showed. So we took median perceived positions from this database. So we just took the median values of each band. So this is all the frequency bands reproduced from the lower loudspeaker layer. And the black dots mean the frequency bands reproduced from the height loudspeaker layer. So we have naturally different degrees of vertical image spread. Even if we just play the sounds from lower loudspeaker layer only and height loudspeaker only, we hear different spread of image vertically. And now we apply some different PBA schemes to create different degrees of vertical image spread. So in this case, we can have this much spread. In this case, we have smaller spread. And this third condition is we just basically split the signals into 2 bands. So anything below 2K, well, from 2K onwards, they are presented from the high speakers. And from 63 Hertz band up to 1 kHz band, we produce them from the lower loudspeakers. And this is hypothetical image spread created by this scheme. And this is the reverse of the previous condition. So we send all the lower frequency bands to the high speakers and higher frequency bands to lower speakers. So we can have reduced image spread like this. And from listening tests we conducted, we had this result. So people clearly perceived different image spread. So we have 4 statistically different degrees of vertical image spread. We have, interestingly, the height-only condition. So when we send all the frequencies, so all the signals are produced from the height layer only, it was found to be the most wide condition of all stimuli. And in order to understand the result, we have to understand how the ear input spectrum, the spectrum of ear input signal looks like, how the spectrum of lower loudspeaker signal and high loudspeaker signal differ in terms of HLTF. So this is delta spectrum from calculated from MIT KIMA HRIL database. So this basically shows that at around 4K, 2 to 4K, the main layer, the sound reproduced by the main layer is more dominant around 2 to 4K. It's got boosted energy around 2 to 4K. Whereas the height layer signal has more energy around 8K. So this is what happens at our ear position. So having this in mind, we can go back to the result. Just looking at comparing between the height layer only condition and PBA1 condition. The only obvious difference between these 2 conditions is the position of the 4K band. So height only has got 4K produced from height layer speaker, whereas the PBA1 has 4K reproduced from the main layer speaker. And 2K as well, 2K. So, having looked at the HLTF difference, we can see that this PBA1 condition has got more dominant energy around 2 to 4K because these bands were reproduced from the main layer, which has more 2 to 4K dominance. So then it's possible that the perceived image is more focused around somewhere in the middle position rather than being more spread. It's more focused around 2 to 4K. And that's where our human hearing is most sensitive to anyway. So that's maybe why PBA1 condition was perceived less spread than the height-only condition. So then what my question that, okay, what's the point of applying PBA schemes and send different frequencies to different speakers? We can just send all the signals to the high speakers and then it will be perceived most enveloping and immersive. Okay, this is specific to this vertical loudspeaker condition only. So when we look at this vertical image spread, okay, the height-only condition can be perceived most spread, but when it comes to the overall 9.1 or 22.2 3D music production, we can't ignore the importance of the horizontal speakers because the horizontal listening envelopment is mainly produced by the horizontal loudspeakers. So if we don't use any of these horizontal loudspeakers to produce envelopment, we might miss something very important. Even if we achieve vertically spread, vertically more enveloping sound, we will lack the horizontal enveloping sound. So we have to think about the overall impression when it comes to the actual mixing system design. So using PBA schemes, we can evenly distribute different frequency bands to different speakers, and when they are reconstructed at the ear positions, they sound quite natural and very pleasing. And it was found in a preference test and also some pilot test we conducted using musical signals. We compared different PBA schemes with 9-channel original recording made using microphone techniques. Even though this result can be very specific to the microphone technique we used to create 9-channel recording, it at least suggests that PBA scheme can be used for mixing, and people generally prefer this method to original recording sometimes. Okay, right, so I'll quickly move on to phantom image elevation now. So the PBA was most relevant for vertical unmixing or 3D content production, and this phantom image elevation theory is most relevant to 3D to 2D down mixing or 3D sound production without high channel speakers. Okay, so let's go back to research finding from 1947. A guy called De Boer, Dutch guy, I guess, he found that phantom center image is perceived to be elevated, and the elevation angle increases as the loudspeaker base angle increases. So this paper was kind of hidden somewhere. It's very difficult to acquire this original paper. I had to contact British Library and so on, because all the papers are difficult to find, but there are so many treasures hidden in all the stereo papers. Actually, funnily, when I found this phenomenon, I thought I was the first one who found this, but it was not. I had to check and everything, and then I found this paper. He was the first who found this. When the speakers are placed right next to your ear, side by side, and you present a coherent signal from both speakers without applying any level difference or time difference, you basically have image perceived somewhere around there, naturally. So this effect has been confirmed by Damask and Mallet in 1969, and only recently some people have, without noticing these papers actually, they found that, okay, phantom images are elevated when they are produced from loudspeakers with a wide base angle. But all of these research used band-limited noise signals. So we decided to repeat similar tests using an extensive range of practical sound sources and controlled sound sources, including speech, helicopter, airplane, thunder, rain, bird, and church bell. All of these are likely to be heard in an elevated position in real life. And these are likely to be used for film, like when you have overhead channels, you might put a bird sound overhead, a church bell overhead. So let's see how these are elevated. Let's see how the old research findings thrown out. Let's verify that. So we conducted this test and also included some noise conditions. And this is the loudspeaker layout. So we varied the loudspeaker base angle from 0 degree to 360 degrees. So mono center and normal 60-degree loudspeaker setting, 120 degrees, 180 degrees, 240 degrees, and so on. So the 240-degree base angle condition, this is in the range of the ITUR 5.1 surround rear speaker position. So this is the response method we used. Basically, there are 12 regions, and people just pointed where people heard the sound reproduced from the specific speaker condition. So this is the overall results, including all sources. This is the front, above back, back high, back, and back low. So as the loudspeaker bass angle increases, basically the perceived image generally elevated like that. So that basically verifies that the early findings are still valid with practical sources, but wait. There is a very important aspect we found, which is the sound source dependency. There was very significant difference in the pattern of subjective responses on how people perceived this elevation. So with transient white noise and rain, the actual pattern is quite linear, and all the median points, they are actually they increase as the bass angle increases. They're quite linear, even though you see some anomalies and like some outliers. So when the spectrum of source is broad and flat, like white noise, rain has got a very similar spectrum as white noise, and the elevation effect is very effective. But with sound sources with more low frequency dominance, like continuous pink noise or speech, the linearity is not as good as the previous sources. You see some patterns non-linear, and there's no above perception for 180-degree loudspeaker phase angle. So we don't have similar results. Similar things happen with airplane and thunder. They mostly have low frequency energies rather than high frequencies. Bird and bell, these are interesting because bird has got really narrow spectrum. It's just around 2K and some harmonics. In that case, it's very difficult to have consistent elevation perception amongst different listeners. Bell has got steady state, kind of like more like a pure tone kind of sound. And research suggests that pure tone or steady state sound is difficult to localize anyway. Another important thing you can think of is the expectancy bias. Speech, you don't really hear speech from above mostly in real life, you know. I mean, unless you hear voice of God every day, you don't really hear everything, you know, from directly above. And even now, you're hearing my voice from the top mounted speakers, but you don't probably think that I'm speaking from the ceiling, you know, because we always hear speech from, you know, horizontal plane or maybe just slightly elevated position, like announcement speaker in stations or whatever. So maybe there was some kind of expectancy bias in our experiment. When it was difficult to localize sound, people would just probably go for whatever they're used to. Okay. These results can be physically explained by looking at this. How much do I have? 5 minutes, okay. Yeah. Yeah, so we talked about the directional bands by Blauert. 8K is mapped to above perception. Let's see what happens as the loudspeaker bass angle increases. So this is delta spectrum, delta HLTF. Basically, I subtracted HLTF of each loudspeaker bass angle signal from the 0-degree mono center HLTF. And this is what happens. So as the loudspeaker bass angle increases, the 8K energy increases, whereas the 4K energy decreases. So if you remember what 4K and 8K do in terms of directional bands, 8K provides more aboveness. I don't know if it is the right word, but aboveness for 8K and frontness for 4K. So when you spread the loudspeaker bass angle, then the frontness decreases and aboveness increases. And this above perception can be quite effective even with 240-degree loudspeaker bass angle, which means that in 5.1 production, if you just send your guitar or whatever to real speakers without applying any panning, just mono signal, dual mono to left and right real speakers, you'd probably hear things elevated directly above or an above back positions, depending on the spectrum of your source. So that could be very effective and useful in down mixing situation where you don't need any high channel speakers. This is extra thing, but I'll probably skip it very quickly. Directional theory, directional band theory doesn't fully explain this phantom image elevation effect because that's more relevant for high frequencies. But we certainly hear elevation effect with low frequencies as well. So that's provide a new hypothesis on this based on acoustic crosstalk. So in stereo listening, we have this acoustic crosstalk. Left ear receives sound from both loudspeakers, and this blue signal, the contralateral signal, can be regarded as acoustic crosstalk, and there's a delay between the direct ipsilateral signal and contralateral signal. This acoustic crosstalk delay might be interpreted by the brain as shoulder reflection. That's something like this. The brain might be confused in understanding what's going on, between two ear input signals. When there's no interaural difference and there's some acoustic crosstalk going on, the delay time could be interpreted by this as shoulder reflection, which is known to be very important for elevation perception for frequencies up to 3 kilohertz. Research by Algaz et al. Suggests that. So when you have wide base angle, the delay increases. And this is the same situation as when the real speaker position goes directly above the head. The shoulder reflection becomes maximal. So they are all in the order of 0.7 milliseconds. So shoulder reflection increases, we hear more elevation, and when loudspeaker base angle increases, acoustic delay increases, and then we hear things similarly as in a real source situation. That's a new hypothesis I provide, but of course it needs to be verified and experimented. So low frequencies, we might use some cognition, basically. We perceive things cognitively rather than in a hardwired way. Whereas at higher frequencies, we rely on HLTF, directional bands, just directly tell us that, okay, AK is dominant, so it's supposed to be above you, that kind of thing. So maybe it's kind of hybrid between this cognition and hardwired fact. Right, so I'll quickly summarize my talk. So perceptual mechanism of vertical stereophony is different from that of the horizontal stereophony. So we need to think about new methods that are optimized for our perception for vertical sound. And using the PBA method, it's possible to render different degrees of vertical image spread, and it can be preferred in terms of quality, and also it can be useful for 2D to 3D unmixing, especially ambience unmixing where you don't need accurate localization. You just want to spread the sound, then this method can be useful. Virtual overhead perception using loudspeaker arrangement, specific loudspeaker arrangement like 180 degrees or 240 degrees, somewhere in between. They provide you with this virtual elevation, so they can be used for 3D to 2D downmix, 3D production without using height channels. Right, so ongoing work. This is our newly built TUL 1116 listening room. It's capable of up to 24.2 3D reproduction. We've been doing some experiments in this room to further the development of PBA for 3D audio renderer, and using the phantom image elevation effect, we can actually have some panning in virtual upper hemisphere. Once you have this image above you, you apply some delay or level difference between two speakers, the image goes like this in a circle. And then you apply some you apply some level relationship with the center speaker and the side speakers. You can also have some panning this way as well. So you can kind of make the image appear wherever you want. Of course, there's no accuracy here. It's for flexibility and creative purpose. So this virtual upper hemisphere panning is being developed. We're also working on new recording and mixing techniques for virtual reality applications. I'm running out of my time, so just skipping. Basically, yeah, what we are trying to provide is a theoretical basis, a grounded theory for the development of intelligent 3D music production techniques. And I live between two worlds of theory and application, and I'm a recording engineer and musician myself, so I want my research outputs to be used for practical applications. So if you are doing practical music production, and if you want to use any of these research findings, please let me know. And I always welcome the ideas of collaborations. If you want to use our facilities to test your mix or whatever, just contact me. And yeah, just to introduce some free softwares we developed for researchers. So this is universal listening test interface generator. You can create whatever listening test interface you want to create. You don't have to start from scratch. You can have very easy and quick way of creating your interface. This is all Maximus based. This is called HART. You can measure impulse responses up to 24 channels all in one go. You just create this. You have this interface. Press one button. Measures all the impulse responses using 24 microphones and 24 speakers. And this is a new panning interface, immersive audio renderer. There's all 3D loudspeaker panning and audio binauralization as well. And this is what George mentioned before, but perceptual time amplitude panning uses both level and time differences, and you just pan your image position to wherever you like, and then you can also change the ratio between level and time. So if you use more time, then you have more wide image and more spread image. If you use more level, then you have sharper and more accurate localization. But the image position stays at the same position, controlled by this dial. So they're all freely available. So if you're interested, just contact me, and we can talk about in what ways we can collaborate, or you can come visit Huddersfield and try your 3D mix in our facility. Thank you very much for your listening and your patience.